All right, thanks everybody for coming today. I'm really happy to introduce Marianne Karplus, who's a professor at UT El Paso, just down the road, but like kind of a long road away. Marianne comes from Dartmouth College, where she got her undergrad, and then Stanford, where she got her PhD. She works on a broad range of topics related to active and passive source seismology, tectonic structure, but also getting into a lot of glacier seismology as well, which is exciting to me. She's also really dedicated to improving the life of students at UT El Paso, which is primarily serving a lot of first-generation students, and she's taken a huge number of first-gen students to Antarctica for the first time, which is pretty amazing experience. And she's also, when I Googled you, I found out you're a published poet, which is pretty cool. So please join me in welcoming her to talk about her project in Antarctica.
Great. Thank you very much, Ginny. I think is the mic's working, I think. Okay, great. And so thank you very much for the invitation. I know I know many people here from a variety of different environments. I did my postdoc in marine geophysics and seismology, and have done a lot of work in tectonics, and recently also some work in near surface geophysics out in West Texas and critical zone scale. So I have a broad range of interests. Today I wanted to talk about a project that's consumed a lot of my time and been a huge collaboration over the last 6 years. And it's one of a number of international Thwaites Glacier collaboration, or ITGC, science projects that were funded in 2018. I'll talk a little bit more about that. But the project that I'm part of is basically focused on the shear margin of Thwaites Glacier. So we're trying to understand why the shear margin is where it is and whether or not it might shift in the future. And I for this specific talk, actually, one of my students who's been looking a lot at seismic data we have from Thwaites has found a few interesting clusters of earthquakes. And so the tectonics part is very relevant to the ice flow. There's a lot of complex tectonics underneath Thwaites, but it's also sort of an interest of mine as well. So looking at the rift system in West Antarctica and some potential tectonic seismic events. And I wanted to just acknowledge the huge range of people who've worked on this project. I'll talk a little more about the details. A lot of people have gone to Antarctica to do field work. There's also a large modeling component of this group. So we basically have a seismic team, a radar team, a modeling team, and have worked with just a wide range of people over the last 6 years, and it continues as ongoing work. I wanted to mention the lead PIs on the project. So each of the Thwaites ITGC projects has 2 lead PIs, one in the US and one in the UK. They're joint NSF and NERC funded projects. And in the US, the lead PI is Slavik Tulacic at University of California, Santa Cruz. And in the UK, the original PI was Paul Christofferson. He moved to Tasmania, to UTAS. And at that point, TJ Young, who started as a PhD student on this project and is now a faculty member at University of St. Andrews in Scotland, he became the lead PI for the UK side. But as you can see, there's a broad range of radar, seismic, modeling scientists working on this project. And I wanted to start out with some sort of general motivation for this project and for working on glaciers in Antarctica. And I'm sure you are all familiar with Antarctica. This is just kind of showing you the scale of Antarctica relative to the US. I often tell people out in El Paso that Antarctica is the size of 20 states of Texas. Maybe you tell people the same thing here. But there's also just a huge amount of ice in Antarctica, as I'm sure you all know. So 2 to 3 kilometers of ice in many parts of the continent. And it's, as you can see, the size of 20 states of Texas. And so part of the reason why we're looking at Thwaites Glacier specifically with all of the ITGC projects is it's a very large glacier. So it's the size of the UK or the state of Florida. And it's been shown to be it's both currently contributing to about 4% of global sea level rise. And it's also one of the glaciers that's been identified as at high risk from both being in West Antarctica, where a lot of the bed is below sea level. I'll talk a little bit more about that later. It's also an area that's been documented to be warming quite a bit, and it's a very fast flowing glacier. And so all of those things contribute to a great concern about the glacier. And the media sometimes calls it the Doomsday Glacier. I don't like that terminology for a number of reasons, but it's kind of highlights the broad importance of the glacier. And I just wanted to say just a few words about ITGC in general. Actually, a couple of years ago, I joined the Science Coordination Office of ITGC as a co-PI. So I've also been involved a little bit in the general, organizing meetings for the project and some of the broader project management. So ITGC overall is 8 different research projects. You can see in the map here where those projects are working roughly. So there's a number of ocean projects, ocean-based, ocean ice shelf projects, the ice shelf, and then GHC, geological history constraints. They're working on a variety of nunataks and places where you can see outcrops of rocks in this area. And then I'm part of the TIME project looking at the eastern shear margin. And there's also another project looking at the upper ice sheet called GHOST that is working on sort of the upper trunk of Thwaites. These efforts started quite a while ago. You probably noticed from the time frame, a lot of them were heavily impacted by COVID, especially TIME and GHOST, which were originally asked to delay a few years for our field work. And so we ended up kind of really being impacted, and sort of everything was stretched out and extended because of COVID, and we didn't get all of the data we had hoped to collect, but we did, after this last field season, we did get a lot of really exciting data. So we're grateful for the data that we were able to collect. And I just wanted to highlight this is a very remote area, and it takes multiple flights to get to this location. We're working out of small camps, and those types of logistics really benefited from the international collaboration with the British scientists and the British logistics of the British Antarctic Survey. And so I mentioned before that a lot of Thwaites bed lies below sea level. So this is an image, sort of a cross-section through glacier, could be Thwaites, with a retrograde bed slope. And so there's basically concern that so a lot of the melting comes from the warm ocean water that's impacting the ice. And so as you allow more and more of the warm ocean water to come underneath the ice, and you have a greater surface area of ice exposed to the warm ocean water, it has a significant impact on the melt rate. And there have been some very striking papers from other groups, including other ITGC projects, as well as others working on Thwaites. There's many other groups working on Thwaites outside of ITGC as well, that have shown huge cavities underneath Thwaites, and looked at processes of basically how this warm seawater gets pumped up under the ice. And that's all of those seem like very important processes for how the ice is exposed to warm water that then leads to melting. So in this schematic, the part of the system that I'll mainly be talking about is fairly far from this dynamic part of the ice that's interacting with the ocean. We're working up on the eastern shear margin, and where you have mainly ice processes and ice rock processes underneath. So we're very interested in the bed beneath the ice, as well as the shear margin and how that impacts the ice and how it may be controlled by the bed underneath. And I just wanted to just briefly show this picture. So this video or animation from NASA that shows the flow of ice within Antarctica. So I just wanted to mainly point out this. You can see this is Thwaites here, this large kind of blue and pink area. So it's sort of highlights so in the center of Thwaites, many parts of Thwaites are flowing at several kilometers per year towards the ocean. And so, but I love this video because it shows sort of this beautiful network of channels and rivers, and how, this is going to zoom in a little bit more on Thwaites, how the ice moves from the central part of the Antarctic continent out towards the coasts. So you can see many areas where there's relatively little ice movement, including just off the edge of the Thwaites shear margin. So just right there where we just lost that, we're going to look at some other glaciers, but I just kind of wanted to highlight that because it shows really beautifully the ice flowing out from the central part of Antarctica, sort of this network of channels or arteries that allow the ice to move. So I talked a lot about the bed under the ice and how we're looking at this dynamic place at the edge of Thwaites Glacier, where basically you go from flowing ice within the glacier to not flowing ice off the edge of the glacier. And so that's shown here. So this is a map of the bed under the ice from Bed Machine. And then on the right is the ice flow speed. And the two little clusters of triangles, these are actually showing our 7-station broadband seismometer networks. But I wanted to highlight here that we basically set up our field element of our proposal was to set up 2 geophysical observatories at the edge of Thwaites across the shear margin, and then to look at also some measurements in between them. So we do have a few measurements between the T1 and T2 site, but some of our, because of some COVID-related and other challenges with logistics, we ended up only collecting active seismic data at the T2 site, and then we weren't able to collect as many measurements in between as we had hoped. We mostly worked out of camps at these individual sites. But we collected a lot of quite interesting data that I'll show you. And I just wanted to mention, so some of the motivation behind this came from Joe McGregor and others here at UT, this is a paper from 2013, looking at the eastern shear margin of Thwaites Glacier and basically noticing that, so you can see this black line showing the eastern shear margin, and then the right map is showing the strain. And then over here, you can see zoomed in on the shear margin. You see, and the background here is the ice flows, is the subglacial geology, the elevation. And you can see here that there are changes in the subglacial geology along the shear margin. And what they showed in this paper from the radar data, and I'm just highlighting the locations of T1 is the purple star. That's the closest radar profile here to T1, and T2, the closest radar profile, is shown with the green star. But you can see pretty different environments in these two places. And there was another paper by Dusty Schroeder when he was here, he's one of our co-PIs on this project, that was also suggesting that at the T1 site, it may be controlled by hydrology, the location of the shear margin, and at T2, the location of the shear margin may be controlled by thermal characteristics within the ice. So this was sort of part of our initial motivation, was looking at, in this area along the shear margin where there's relatively little change in topography, at least no sort of consistent change in topography. Some of the, like the Bird subglacial basin, which is this blue topographic low, it cuts across Thwaites. So the flow of Thwaites is kind of is plowing across the top of these sedimentary basins and not necessarily along them, like in some other glacial environments. And so we thought this was a very interesting shear margin because of this sort of changes in the properties along the shear margin and the potential to look at why the shear margin is where it is when you don't have topographic controls. And then from a sea level rise perspective, and from a stability of the West Antarctic ice sheet perspective, we wanted to look at whether or not the eastern shear margin could be susceptible to lateral migration, which was an idea presented in this paper based on the relatively weak control of the bed on the location of the shear margin. And of course, if you move the shear margin, you could suddenly have more ice or less ice flowing rapidly towards the ocean. So it could make a big difference for stability of West Antarctic ice sheet and sea level rise. So in the proposal, we suggested to collect a variety of different types of data. I mentioned seismic, radar, GPS data, and then there's also a strong element of modeling. Because of the way that the fieldwork got very, very extended, and we just finished this year, we've had some modeling that sort of happened in parallel with field data collection, but we have a lot of work to do still to bring everything together. And I'm mainly showing you a little bit of like a fairly early snapshot of some of the data today. And I just wanted to sort of highlight some of the sort of changes in the plans for this project. So this was our planned proposal. It looked relatively modest, 3 field seasons, still a lot of work represented there, but it would have been 3 field seasons with radar, 2 years of a broadband seismic deployment, and then the second 2 seasons would be the controlled source seismic surveys during those seasons. And then we'd have a couple years to wrap up and we'd be done in 2022. So that's not actually what happened. So we were asked to delay even before COVID. And so we asked for a small supplement to do some source testing. And this was actually my first trip to Antarctica, was just with one other team member. We were with Galen Cape at the seismic source facility at UTEP at that time, now at EarthScope. We did some comparative seismic source testing. We published a paper on that, looking at different types of explosive sources on ice. Then in 2019 to 20, there was a field season deploying about 3 weeks, deploying broadband seismometers and the GPS stations. We were again asked to delay the active source. So then COVID happened and we had our stations were out getting buried in snow, but we were not able to send a science team to Antarctica. In 21 to 22, after more than 3 weeks of quarantining, we were able to get down to Antarctica. It was very impacted by various logistical problems, lack of staffing and things, because everyone had to go through the managed isolation and quarantine in New Zealand. But we did field a team for about 2 weeks, and we worked extremely hard and got extremely lucky with weather, and were able to demobilize the whole network. They told us just to get all the stations out. We still can't do the active source, but you need to take all your equipment out. So we did that in 21, 22, and that's when we got all the passive seismic data back and the GPS data. And then in 22, 23, we tried to do a controlled source season. Our team size was cut, and our cargo to the field was cut, such that we were not able to have enough time or personnel or equipment to do the active source. So we did anything we could. We deployed a lot of seismic nodes for 8 days while we were in the field. And then finally, in 23, 24, this is a bit of a dramatic photo, but we were able to do some explosions. This is the Poulter surface seismic shot that's very zoomed in with a very high magnification camera. But basically, we were finally able to do some of our controlled source seismic surveys, which was initially the part of the project that I'd been planning to work on. I've ended up doing also some passive seismic work that I'll talk about today as well. But I wanted to highlight that, there's a lot of challenges and logistical changes, as always happens with Antarctic fieldwork, and maybe especially with COVID. I know a lot of people have been impacted over the last number of years and will continue to be in the future. But some of the silver lining is, I think we had 17 Antarctica first timers as part of this project, myself included, people who had an experience to go to Antarctica, were able to go to Antarctica to conduct field work and collect data for their PhDs and postdocs and masters in one case. And so that's very exciting. And I think in total, a lot of these were very long field seasons. I just wanted to acknowledge that. I realized in total, I spent almost a year of my life in Antarctica for this one project. It's my only Antarctic project. So I have a lot of other projects, but overall, it was, there were a lot of challenges, but I really enjoyed the opportunity to work there. And I'm really fascinated by the data that I'll show you shortly. So today, I'll talk a little bit about the 2-year broadband seismic deployment and some of the tectonic related seismicity we're seeing from that. And then I'll talk a little bit about the new 2D and 3D seismic profiles that we collected just this past season. So that's very, very new data. It's still ongoing work. I just wanted to highlight that these are our camps from 3 of the seasons. The last 3 years, this is my first Halloween not in Antarctica since 4 years ago. But yeah, so we did all of this work out of these remote camps with, that were basically relatively unsupported, just with mountaineers and our science teams. And so I'll talk today about work that's I'm working on with my PhD student, Lucia Gonzalez, on the passive seismicity. We're also working closely with Jake Walter, who was here before. He's now in Oklahoma. And then I'll talk a little bit of work that's being led by Danny May, a PhD student at Stanford, that we're working on together. And then the 3D seismic imaging is work by Zhendong Zhang and Nori Nakata and myself and our team together. And so just a little bit more on the motivation. So I just wanted to highlight, so specifically for the seismic part of this project, here's a number of things that we're looking at with the seismology. So this includes what the seismicity can tell us about movement of the ice, stick slip movement, crevassing, fractures, tremors, information about the sub-ice geology, which is mainly what I'll highlight today, the bed material, temperature. So I mentioned we're trying to look at whether there were temperature impacts on the location of the shear margin, the bed roughness, as well as the ice crystal orientation, such as englacial reflections and anisotropy. And this is a picture from, I think, Paul Summers from our modeling team, who is a PhD student at Stanford. He's now a postdoc at Georgia Tech, and looking at, kind of highlighting the physics of what's going on at the shear margin. And so the next section, I'll talk about the passive broadband recordings of seismicity. And I mentioned the season where we were digging up stations from beneath the snow after the COVID year when we couldn't service them. And it required writing a lot of poetry. We were very concerned we weren't even going to get to the instruments. So I had never written a sonnet before, but I wrote a sonnet because I was very it seemed like the right type of poetry for this particular case when we were waiting in McMurdo to like hopefully get out to be able to dig holes like this to get our seismometers back from the ice, and so they wouldn't be lost forever. It represented, I think, $1.2 million of seismic instrumentation from EarthScope as well. So we were very motivated to do everything we could to dig these out of the snow for that reason as well, since it's a community facility. And with seismic data, there's a variety of signals we can look at. Mostly today, I'll be looking at some of our lower frequency signals from that we are interpreting as tectonic earthquakes, but this is just showing you the basic setup of the instruments. And then I wanted to give a little bit of background on history of seismicity and seismic studies in West Antarctica. And so this paper from 1987 by Johnston suggested that there was actually very few earthquakes that were observed in Antarctica at that time. There was a suggestion that maybe the ice sheet was suppressing continental earthquakes at that time. Here's another study in 2003 that was, I think, the first paper suggesting some tectonic related earthquakes in West Antarctica in the West Antarctic Rift system. There's relatively few, even still, that have been observed. These are, just for reference, Thwaites would be kind of over here. So we're working more in this region, around 100 west. So there have been a few earthquakes that were recorded here. Again, there's very relatively little seismic data at this time in 2003 when this paper was published. They had a small network out for those 5 stations there for a couple of years, 98 to 2001. And then here's a more recent paper from 2021 using some of the PolNet network in West Antarctica. They've done an amazing job at increasing the seismic coverage in West Antarctica. And you can see, so Thwaites is the blue outline here. There was this little green event, which the green is tectonic. So they interpreted this 3.5 magnitude earthquake as a tectonic event, a normal faulting event beneath kind of the central part of Thwaites Glacier. And then they found a few other tectonic events in the Ellsworth Mountains, the other little green dots. But you can see there's a lot of different, once you dig into the signals and identify sort of different glacial signals, there's volcanoes under the ice sheet here. There's a lot of different seismic signals to evaluate. But then this is 2 years of data and a relatively sparse network. And so I think they had 114 earthquakes that they looked at in this study. So there's still relatively little seismicity compared to some other rifts, like the Western Arctic rifts about the scale of the Basin Range sort of rifting. There's a lot more earthquakes that we see in the Basin Range. So there's some question of, is that because of instrumentation, or is that because the rift is less active, or so it's a kind of interesting question for the tectonics as well as understanding the geology under the ice. And then this is sort of a most recent study where Peña Castro et al. In University of New Mexico kind of took all the seismic data from the 20 years from 2000 to 2020 from Antarctica and came up with this new catalog of seismicity that was sort of done in a standardized way. And they found a variety of events, a range of different kinds of events, icequakes, earthquakes, but you can see here that some of the distribution of those events that they found for the Thwaites Glacier area. So Thwaites is kind of this area here. And so this is showing the ice flow on the left and the bed underneath the ice from bed machine on the right. And you can see here these little clusters that my student Lucia has been working on, these little blue dots. So this is, we, basic, so, and this is to the noise environment. I just wanted to highlight it's pretty quiet out there in West Antarctica, where we have our network. So it's near the low noise model, closer than the high noise model, those of you who are interested in seismic data. So we basically went through the 14 stations and we used the EasyQuake package that Jake Walter developed, but it's basically wraps around 3 different neural network based machine learning seismic phase pickers. And so using those phase pickers, we actually decided to use all 3 of them and then remove the duplicates and kind of put together a catalog from all 3 of them. And you can see here just some examples of the data and the from this process. And then this is showing you all of the locations from the picks from EQ Transformer, GPD, and PhaseNet, the 3 different machine learning based pickers. So they're colored by which one found the event. So you can see quite a bit. Some of these are very small events, like -1 even, but there's quite a bit of seismicity that we've been digging into in this area. Probably some of it is related to even calving at the ice front, even though that's very far away and very difficult to locate with these distant networks. But we do have these little arrays. So the little 7-station arrays can help with the location of events outside of those networks. The array geometry was largely controlled by logistics. Like we couldn't leave this area, so we had to snowmobile to an area to put out stations. So then from the data that I just showed you, we decided to focus in on a couple of clusters that looked interesting near the T1 site. So that's what's shown here in this map on the lower left. And this is showing you the locations after we did we ran matched filter detection as well. So we had 92 events that we picked out that we decided to run the match filter detection, and then that yielded more than 1,500 events. And so it was detecting a lot of similar kind of events that looked like those initial 92 events that we had found. And after doing the matched filter detection and having this 1,757 events, and I should say also, I'll show it in a minute, but these events, some of them are outside of the network, a lot of them are outside of the network, but the depths we were getting are all kind of 7 to 10 kilometers. So we were like, okay, these really don't look, and we looked at several of them, and it seems like they're a little bit, they are, 7 kilometers depth. After doing some tests on that. So we started to think, okay, we were thinking we might get a lot of icequakes. Maybe we thought a lot of those events may have been icequakes at first, but then we started to recognize that probably this cluster, and they're mostly relatively low frequency events. These were between 2 and 14 hertz was the filter that we used for this detection, or for the initial detection with EasyQuake and with those machine learning based pickers. But if we look at some of the statistics for this catalog, you can just see that up here, the Gutenberg-Richter relationship, we got a b-value of 1.08, which is kind of standard for tectonics. I know you can't always say anything related to b-value, but it made us think again, like, okay, this seems like a typical-ish tectonic earthquake cluster maybe. And you can see here in the map, a lot of the events are along this, this is a little hard to navigate. Along this line is the edge of the Thwaites drainage basin. So it's basically a drainage divide where that's been identified from previous work. I think this was a paper from 2013 where they identified this specific region as the Thwaites drainage divide. And so we started to wonder if could there be a process happening in that area that might be linked to these earthquakes. And then we had this little cluster right underneath our network as well. You can see a couple of these little earthquakes very near, right underneath our network at T1, which was part of the reason for focusing on these. So here's a little bit more so we did a relocation with HypoDD, and then this is showing you the events relocated from HypoDD. And again, you can see it still looks like they kind of follow along this drainage divide. And if you look at them in cross-section view, so this is from A to A prime is this direction. So the grid east-west, and B to B prime is grid north-south. And you can see here that most of the events are, like I said, around 7 to 10 kilometers in depth. And then there's a couple of events that are identified here that might be in the ice. In this area, the ice is 2.2 kilometers thick, roughly. And then you can just see that in this this is showing you like that after hypo DD, it looked like a very tightly clustered set of earthquakes, about 500 meters across, which is interesting. A lot of very small events, but up to 2.3 magnitude. So these are some of the events that we're interpreting. So we have kind of the seismicity cluster 1, about 25 kilometers from T1, and a seismicity cluster 2 just beneath the network. And then this is showing you more statistics. So we noticed, not sure if it's significant, but we noticed there's more events kind of in the middle of the night local time. Maybe a temperature. I mean, it seems like it shouldn't be a temperature relationship when it's a or something like that when it's a tectonic events. But anyway, we're just looking at the data in different ways. It could be sometimes the decrease in an apparent decrease in events sometimes reflects more noise in the data. So it could be just it was noisier during the day, so we're not detecting as many events. But it's unclear why, unless most of the year it would be just things like wind that would be causing those noise in this area. And then for some reason we also see more of these earthquakes in October and November compared to the rest of the year. Again, it could be related to the noise on the stations or something else, but we're just kind of looking at the data in different ways. And then you can see also the depth profile on the far right for those events. And then in terms of thinking about what's causing the earthquakes, so I talked a little bit about the Western Arctic Rift System. I just wanted to show a couple of figures showing you this is from a recent paper by Tom Jordan and others looking at the tectonic evolution of the Western Arctic Rift. And so you can see here this extents of the Western Arctic Rift. It's a large region about the size of the basin and range in the Western US. In West Antarctica, beneath the ice, there are volcanoes in parts of it, mainly over sort of in this region are most of the volcanoes. I think they're on, I guess not on this map, sorry. But, and then this, the figures on the right are showing you some of the history of the tectonics in this region. So it's going from back 175 million years when you had subduction you had subduction offshore of this part of West Antarctica. And then stepping through 165, 100, and up to 46 million years when you have, at least in this interpretation, where you have developed the rift already. So you have rifting happening at that time in West Antarctica, the continental rifting. And then you can see a cross-section on the lower right, also of an interpretation of the rift zone when perhaps some of those sedimentary basins were forming, like the Bird subglacial basin. And another, I also mentioned, so maybe some of these are rift-related earthquakes. It's not really been seen before. It's been seen to be a pretty quiet tectonic zone. So then we were thinking, well, could it be related to glacial isostatic adjustment? Maybe especially because the earthquakes are some of them are right below the edge of the drainage divide. And so it's hard to get the detail you might need of the ice thinning in the specific area near the drainage divide, near the edge of the Thwaites drainage basin to look at this. But here's one paper from 2019 looking at observed thinning from 1992 to 2017. So you can see the red colors are showing you thinning up to about a ½ meter per year. And if you look at these, if you have time to kind of look through these time steps, it's showing an acceleration of thinning across the Thwaites Glacier in that time frame. And so basically it is an area where there is pretty significant thinning, and the seismicity paper by Erica Lucas and others in 2021 suggested the central Thwaites Glacier earthquake, that magnitude 3.5 I mentioned, was possibly caused by glacial isostatic adjustment based on significant thinning of Thwaites. So it's another possibility that could, the big changes to the ice could impact changes in the subsurface, probably needs additional modeling and checking for the specific area, but it's an idea. And then you might say, well, what about icequakes? So I just wanted to mention briefly, although this is not the main focus today, but I wanted to mention briefly that we did see a lot of icequakes. A lot of those events, even picked up by the machine learning detectors, are icequakes when we look at them, although those mechanisms are all trained on earthquakes. So we may be getting more earthquakes than some other techniques. And we also filtered it from 2 to 14 hertz. So kind of trying to focus on those frequencies. And but as an example, so here's an example of an icequake. This is one of the more impulsive icequakes. Icequakes can often have a very emergent signal, so they can be challenging to pick up with typical earthquake detection algorithms. But this is showing you just an example with a very strong split S wave. And you can see the P wave arrival and then S wave arrival over here. And we located actually Emma Smith and at Leeds, she was a postdoc working on this, and she's now moved on to another position. But she did a lot of really nice work locating these sort of higher frequency impulsive icequake events using a package called Quake Migrate. And so this is just showing some snapshot from her work, which I won't talk too much about today, but basically showing you a lot of icequakes. So this is also the T1 network. And so it's very near those earthquakes I showed you earlier. But this is, these ones are all kind of locating in the ice or a little bit, a kilometer and a half beneath the ice. And so we're also looking at these data, although it's a little bit less far along compared to the other work that I showed you. And then finally, I wanted to get into some of the new controlled source seismic data that we collected just this past season. So this is very, very new. And we had a lot of twin otter loads of seismic nodes that went out to the field for this. We ended up deploying 1,000 seismic nodes. And that's a lot. It's like every node is 6.2 pounds in weight. So that's 6,200 pounds of seismic nodes. It's a lot of seismic nodes. So I just wanted to highlight that this work is done at T2. So we're now moving to the other shear margin site, which is ended up being the only location where we were able to collect active source data because of the logistics. And I just wanted to mention, when you have 1,000 seismic nodes, you need a nodometer to be able to keep up with how many you've deployed so far. So, and we actually, because of cuts to our time, we ended up having a night shift deploying as well as a day shift. We had a limited number of snowmobiles and equipment, and so we'd end up, having day shift and night shift deployments in order to make the most of the time and the resources that we had. So it was a big field effort to make this happen. We also detonated 671 surface explosives, which was also a big effort. And these were the type of explosive described in the journal Glaciology paper that I mentioned there. And I'll just show you a quick video of the explosive as an example. So that's so typically in Antarctica, we would have preferred to drill these, but we actually, because of logistical constraints, we weren't able to, especially with this number of sources, we weren't able to actually even bring our drill to the field in the end. It was cut as part when we had to cut cargo. And so we had a hot water drill. We were going to drill 30 to 40 meters depth in the ice and load the explosives. And in the end, we were not able to physically have enough cargo space in these small airplanes to bring the drill. And so we did all of our shots as Poulter surface explosions, which the Poulter style is basically like you saw there. It's like a bamboo pole 6 feet tall with an explosive taped on the top of it. And so we did, we had a 2D sort of longer line that was about 27 kilometers long, and that's shown here. And then we had a 3D box crossing the shear margin. You can see the seismic fold over here in the largest fold area. We had 60 fold. So along the long 2D line, we had 181 sources, 50 meter spacing in the center, 300 meter spacing on the wings. And then we had 234 3-component seismic nodes along that long center line with 50 meter spacing in the 3D box and 150 meter spacing outside of that area. And these are this is the 2D profile. So you can see here, the top is a seismic section. The bottom is an airborne radar section. and across almost the exact same line. So we're very fortunate that I think the radar was all flown by British Antarctic Survey and is available now. So we have the airborne radar data almost exactly along the same profile. And so this is actually, I think this is work from Danny May. I think he actually has like a little bit more cleaner image, but he was working on cleaning up. These are probably artifacts of the processing here that I think his more recent image has removed. But I just wanted to highlight here. So the center of this line is where we think from the calculating the surface strain that would be the center of the shear margin. And the fast ice is on these profiles is shown on the right and the slow ice on the left. And as you can see, so this is basically a common midpoint stack across the whole line. So you can interpret this like a cross section if you're not, sort of is one idea of how to look at this. But it's a common midpoint stack from the seismic data. And you can see here pretty clearly the bed beneath the ice. So that's this bumpy interface, and we've overlaid these on top of each other, and it corresponds very nicely, which is always what you want to see with the radar data. The radar data saw this interesting like higher reflectivity underneath the fast ice that may indicate sediments or water at the base of the ice under the fast ice. And we don't see quite as striking a change on the fast ice side in the seismic data, but we do in terms of the reflectivity. But we're still refining the images. So that's just sort of our initial thought. And then there are a few features we're looking at in more detail. One of them is, and actually with looking at the data so we have 3 component data. So we've done some S wave imaging and some P wave imaging. And it seems like you may have this small feature here that our preliminary interpretation is water, maybe saturated sediments. You also see a very bright reflector in the radar. And then there's also some interesting structures kind of here very near the shear margin where you have sort of these maybe offset reflectors, and you see this sort of lower, deeper, high amplitude reflection underneath the surface. And you can also see that in the radar data, which is unusual to see in radar data, like a reflection underneath the bed. So we're kind of looking at that in more detail as well. But as I said, it's fairly preliminary. We're also looking at the roughness and in general, this may not be the best image to see it, but in general, we see an increase in the surface roughness underneath the slow ice side and the seismic. And then we did, so this is Jindong Zhang and Nori Nakata or Jindong has developed a method to do full waveform inversion using primarily using surface wave dispersion and inverting that for a velocity model. And so this is showing results from his work, the methods described in his paper from 2024 in JGR. It's mentioned there. And so this is showing you again the 2D long line. He inverted, like I mentioned, the surface wave dispersion from a variety of modes to look at velocity structure. So we have VP and VS velocity structure, and then VP VS. And I just wanted to highlight there's a lot of interesting things here, including higher velocities on the fast ice side. This is all just top 500 meters of the ice, I should say. So this is just the ice. But then in the area around the shear margin, we see some BPVS anomalies potentially that could indicate low porosity in the shear margin, maybe crevassing, around 100 to 200 meters deep. And then this is showing you the fast ice velocity, 1D velocity profile is the red, the shear margin is black, and the slow ice is blue. And so you can see some of these striking, well, so in some cases they're the same, I should say. And in other cases, like we were quite interested that the fast ice has this about 1.5% increase in the S wave velocity, but not really in the P wave velocity. Another thing that was interesting was for VP-VS ratio, we have this low at about 100 meters depth. And so we're working on interpreting these and looking at other types of data as well from ice sheets to interpret these better. And then the final thing I'll share with you all is some of the results from the 3D seismic imaging. And so this is we had this 3 by 5.5 kilometer box. We had geometry where we had receiver lines that are margin parallel, and we had shot lines that are margin perpendicular. And this was to increase the variety of azimuths. So we will be doing AVO, amplitude variation with offset, to look more at the properties of the reflection underneath the ice. These, just to highlight, so each of the shot lines had 72 shots. Each receiver line had 110 3-component nodes with 50-meter spacing. The shots were also at 50-meter spacing. There were a few additional sparse shots we did around the edges with, they had ordered enough explosives for 2 seasons because we were going to do 2 different active source seismic acquisitions, 1 at each site. And so there was some extra explosives so we added a few of these other shots. With some of those, we weren't able to use all of them. So this is just showing you, so at the moment, the 3D volume that I'll show you is actually missing some shots. They will be added. But in the version I'll show you, it's missing some. We're still sort of working on I think that Zhendong may now have a version that includes those, but in the initial version, they were not included due to a shot timing issue, which has been resolved. It was just in the spreadsheet. And so this is showing you some examples of the 3D seismic data. So each of these is one of the receiver lines, and that's why the middle one is longer than the others. And it also changes in the sparser station spacing on the wings. And so this is showing you a snapshot of those data, frequency spectra. And then this is showing you so we've done the reverse time migration on the 3D volume. So this is showing you 2 to 20 hertz, just vertical component data with a constant velocity model. And so the figure on the top right is showing you which line is being highlighted. And I'll just step through the margin parallel lines. And so you can see sort of the resolution improving. There's a higher fold as you get towards the center of the volume. And then it dies off again a little bit on the other side. But we're pretty excited to have, I think, maybe the first 3D seismic image in Antarctica and crossing a shear margin. And there's a lot here that we're digging into with respect to the reflectivity of the bed, which is the sort of the major reflector you can see here, but also we'll be looking at structures within the ice, trying to improve some of these artifacts and some of the imaging techniques to resolve this kind of 3D look at the shear margin. And then this is showing you we've done the Kirchhoff depth migration for this volume as well. This is with 2 to 20 hertz data, vertical component only. You can see the image looks maybe a little bit cleaner. And then if you look at 2 to 40 hertz, it even gets more crisp. So having the higher frequencies is helping with this image. And like I said, we have a lot more work to do on this and interpretations to do on this. So I just wanted to summarize that. So first I talked about these little cluster of earthquakes you can see here in this shown on top of the bed that seem to be near the drainage divide for Thwaites. And also, we're looking at whether those could potentially be reactivated faults of the Western Arctic Rift or relate to isostatic shifts in West Antarctica. We see from the seismic reflection images that the bed is heterogeneous across the shear margin. It's a bit rougher on the slow ice side, which might be expected if you have sliding of ice over the bed, that it would be smoother. And then the velocity models across the shear margin suggest a larger VS in the fast ice. And there's this interesting high VPVS anomaly very near the shear margin that, while we saw no evidence at all of surface crevassing, may indicate crevassing beneath the surface in this region. We also have just a lot more work to do and a lot of interesting things to do with these 3D and 2D seismic data. So I wanted to, just before I close, I just wanted to say briefly, so I teach geophysics field camp in El Paso. I love teaching field courses. So I just wanted to highlight if anyone wants to talk about education, opportunities for students, field work. There was a paper that I wrote with TJ Young, who we co-led some of these field seasons, and with the broader Thwaites Glacier team about building inclusive field teams and field team environments. So I'd love to talk about those things. And also have done some work in the Himalaya. I have a new paper, a new project looking at glaciers in Bhutan that I'm pretty excited about. And so also love to talk about Himalayan tectonics and ice. And we're also trying to launch a study abroad program to Bhutan for UTEP students. And so where they would go to Bhutan for a few weeks for like a field class, similar to, maybe not quite similar because we can't bring all the geophysical equipment, but a 2 to 3 week field course. I know you all here, we always see the hydrology group from UT Austin in Valles Caldera. When we're teaching our geophysics field camp, they're out there doing resistivity and other methods as well. So anyway, happy to talk about those elements, education and broadening participation and inclusive field teams as well. So thank you very much.
Okay, I'm happy to take questions. I'll start with students if you have questions and postdocs. Nice catch.
Thank you so much. That was a really great talk. So was I seeing correctly that your EQ core scan was picking up some earthquakes that were relocated into above the surface in the glacier?
Yes, there were a few that were in the...
So your filtering, I guess, is kind of picked to avoid these ice quakes. So is there anything weird about those specific ones that are different to the normal ice quakes?
Yeah, that's a great question. So in that work, as well as in the Quake Migrate work that Emma Smith was doing, we were trying different frequency filters, and when we looked at the lower frequencies, it did cut out a lot of the ice seismicity, but not all of it. So that's a really interesting point that I think we haven't. We do see some of the ice seismicity that's more impulsive and that is at those lower frequencies, but I'm not sure exactly what the process is that would be different that would cause those. I mean, it's possible that usually if you have the lower frequencies, maybe it's representing a different ice fracturing process that might give you lower frequencies. I would think of generally like larger events and things like that, but not all of those are very large. So, but it's a great point. I think I don't have a really I'm not sure for those specific events, but I think we should look into that further. So thank you.
Thank you very much.
Hi, very nice talk. And I would like to know, so what do you expect to see? I mean, it's from the seismic experiment at the shear margin. I mean, when you design this project, what kind of the seismic velocity variation and what kind of other features do you expect to see from this project?
Yeah, thanks for the question. So I guess we were expecting from the radar data to see observations like a transition. So the two sites that we had picked to study the shear margin, the T1 and T2 site, one of them had been proposed mostly from radar data, including the work done here, that they had proposed that one of the sites was hydrologically controlled. So maybe you have water underneath the fast moving ice and no water underneath the slow moving ice. And then in the other site, it was it's proposed to be thermally controlled. So I think that in terms of looking at the ice part, like the velocity models, just in the top 500 meters, we're interested in seeing if we can see any changes in the ice temperature from the seismic. And so things like the velocity of the ice could indicate a difference in the temperature potentially, although that's it's not necessarily well connected. So that's one possible way of looking at temperature. Another thing we wanted to look at was fabric and orientation of the ice crystals. So seeing if we could identify, history of the flow of the glacier from the, how well developed the fabric is in the ice in terms of the flow and things like that. So those kinds of things. So looking at fast directions for velocity, I didn't show that in this talk, but looking at even the VS velocity and the VP velocity along the direction of the line crossing the shear margin, there could be changes that are actually representing kind of 3D structure and ice crystal orientations that are different in the fast flowing ice side. So those were some of the things that we were looking at and hoping to understand better temperature, hydrology, and specifically why the margin is in that location where it is, and what, whether, how well controlled it is. So there'd been the previous work suggesting maybe it wasn't very well controlled. And so kind of trying to understand if that margin position could change. And actually one of our radar, TJ had a paper that suggested there was a relic shear margin further out, so that the shear margin may have shifted location. And so if we see along our 30-kilometer line, we could potentially identify past positions of shear margins if they are there. So those were a few things we were looking for in the data.
Thank you.
Yeah, thanks very much. So I was wondering if you can put the bedrock geology map that you showed a few times.
Or sorry,
Yeah,
one?
this one.
That one work? Yeah.
So it looks like there's like gaps where it's not got any kind of contour. So is that related to the rift or to the data? And does it correlate with any of your earthquakes?
So the gaps in between the dashed lines, is that
Yeah.
what you're looking at? Yeah, so the dashed lines are from the paper by Tom Jordan and others interpreting geology at the bed. And so so this is the bird subglacial basin. Or it's, I guess, it's kind of shown here. So this is, the sedimentary basins are in green, and then yellow is mafic rock and red is granitic rock. There's also intermediate rock. So it's a very broad brush, like since we can't access the geology in these areas, this is sort of based mostly on magnetic and gravity data, aeromagnetic, aerogravity, and radar. And it's a little bit of seismic, like there's been pretty clear seismic suggesting the location of the bird subglacial basin. But there's very little seismic in general. Those the techniques where you can fly over are much more, have a much broader coverage. So the areas in between, I think, are areas where they weren't sure exactly, like they weren't able to identify one or the other. And so, so that they've sort of they've identified these bedrock geology, or they've sort of suggested that the magnetics and gravity and radar suggest these types of geology, but the areas in between that are just not from those data. So it was hard to tell what was going on in between some of those shapes. I mean, none of it's very well constrained, I should say. Like this is, if we could look underneath the ice and actually see what's down there, or do more widespread, seismic or other types of surveying, you could get a lot more information about that. But it's sort of doing the best that they did. It's a really nice paper. They did a great job with the data that exists.
Any other questions?
Hi, thanks. Yeah, great talk. Can you rule out volcanism or hydrothermal activity for those clusters near T1?
Yeah, that's a great question. So I don't think we can. So for example, since I live in the Rio Grande Rift, and I know the Socorro magma body in the Rio Grande Rift near Socorro, New Mexico, has a lot of seismicity associated with it. And it's fully beneath the surface. Like there's no recent surface expression of volcanism, but there's a magma body there. The Western Arctic Rift in general, from what I understand from the literature, is about the same age as the Rio Grande Rift and some of the rifting in the Western US, but it's generally viewed to be less active, maybe because of a lot less seismicity, or maybe even not active, except in areas where there's active volcanism today. This is the area where we saw the seismicity is pretty far from any known active volcanoes, but all the geology is below the ice, so it'd be hard to rule out the presence of, maybe there's no active volcano nearby, but there's a magma body or something like that that's beneath the surface. So I would say I don't think we can rule it out. They do look like tectonic earthquakes, but a lot of the small events associated with the magma body, maybe not necessarily with the specific fluid movement of that magma, but just with sort of processes associated with the magma body, they can look like tectonic events. But I think, if anyone has any ideas for distinguishing between those, I think I would definitely be open to that, because, or maybe I'll look a little more. I haven't looked at the waveforms for the Socorro magma body events, but I know there's been a number of clusters of seismicity and some pretty large magnitude 4 and 5 events around Socorro and Albuquerque, New Mexico, related to that. But I think there's a lot we don't know about the West Antarctic Rift, and so it seems to me like an open question of whether we have areas with volcanism or magmatism that's not been identified yet. But we are looking into those clusters in more detail. Actually, I didn't mention it, but some of the events look like they may have been triggered by the South Sandwich Islands earthquakes on August 12th, 2021. The timing is close enough that so we're looking at the data in that way as well, trying to see if you have 2021 was actually a year of anomalously high number. There were 4 magnitude 8 earthquakes in the globe, and several of them were in the southern hemisphere, and there were quite a few magnitude 7s in the southern hemisphere, which isn't always that common. So we're trying to see if maybe looking more at those events, and if those events were sort of, say, triggering some of these little clusters, then that would be an interesting finding as well. But I didn't really mention it because we're still digging into that. So.
All right, I'm gonna cut it off, sorry. But there is one time slot at 1 o'clock if anybody wants to sign up on the Google Sheet that I sent around. And please join me in thanking Marianne for her awesome talk.